Okay. Lester. We have been talking about scheduling, but we always talked about processes. Okay. We said that depending on the priority or the runtime or the preemption or the blocking, we can switch from process to another process. And which process should we switch is decided by the scheduler. We should talk about thread scheduling too in this chapter, because I mean threads are like processes. They are part of processes, but they are different from the processes. There are similarities and differences, and we should consider these similarities and differences when we talk about the thread scheduling. Remember we have two alternatives, or maybe three, but two extreme cases. When we handle the threads at the user space, we have something like that. Okay, we have our thread table at the user space inside the process, and inside the process, the other extreme is that all the thread information is contained in the kernel space. Is contained in the kernel space. So we are going to look at these two examples. In this case, the book says when I am scheduling threads, it is possible to do this in the user space. I will say this is A1, thread A1, A2, A3. This is B1, B2, B3, and B4. Okay. So it is possible to schedule threads using something like that: A1, A2, A3, A1, A2, A3. But it is not possible to do it this way. Why? In the user space, if I implemented my threads in the user space, it is possible to schedule threads like this, but not like that. Yes?
We have no permission to access B1, B2, B2, B3.
Oh, okay. If I am process A, I cannot schedule, yes, process B's threads because it is a process B. So it is the task of the process B to schedule its own threads that way. So that's the reason. That's the exact reason why we can do that. But why do we want to do this? What would be the advantage of doing this? Yes.
If both programs were written by the same team, then they can share the CPU time and make the interactions faster.
You mean process A and process B?
Yes.
Then make both of them into the same process, and they can communicate better without doing any inter-process communication. They can share the same memory. So the process A and process B is written by two different programming teams. It is still, I might want to do this. I might want to do this. I might want to do this because if I do this all the time, then the threads of process B will not get enough CPU time, right? So process A has its own CPU time and process B has its own CPU time. Inside the process A's CPU time, I can run only the threads of the CPU thread A, and inside the B's time, I can run the threads of the B. But if I can do this in turn, A thread, B thread, A thread, B thread, then I would increase the interactivity of these threads, right? I would increase the interactivity of these threads. So with this kind of scenario, it is possible to do this, but not possible to do this. I might want to do that. And if I switch to kernel space threads, then it is possible to this and also this. Okay, both of them can be done. So the advantage for this one is I can increase the interactivity of the threads of A and B at the same time. Otherwise, if I can, in this one, I can it is still possible to do this. It is still possible to do this. A1, A2, A3, A1, A2, and then B1, B2, B3, B4, and it goes like that, right? So this is the process A time, and this is process B time. I am still running the threads of the process B, but I have to wait for the process A to finish its quantum, or I need to wait for the process A to block, so that I can run the B threads. So it is possible to run it that way, but I want them to be interleaved, A, B, and AB. That would increase my interactivity, and it says that. Okay. I can do this, I can also do that. But there is a problem with this kind of run. What is the problem with this one? Sometimes this is better. A1, A2, A3, A1, and B1, B2, B3, B1, etc. So run A, then B. Process A and process B. Sometimes this is better. So when do we prefer this kind of a thread scheduling scenario? Sometimes this is better than this. This is better in terms of interactivity, right? This is more responsive. Okay, because the threads of B doesn't have to wait for the threads of A. But this has some advantages. What is the advantage for this picture?
Less complexity.
Less?
Complexity.
Yes, that's the exact point. With this one, we don't switch context, we don't switch address space. Address space stays the same. When I switch between the thread from A1 to A2, all I need to save is the registers and the stack, and that's it. Program counter, etc. But when I switch from process A to process B, there are lots of other things that I need to say, like the switching the address space, memory maps, changing the memory maps, saving the memory maps and the cache stuff, that kind of stuff. So this has, if I switch between A1 to between A1 and B1, switch between these two threads, and I have to do a full context switch. And full context switch here, and full context switch here. In this case, I don't do any full context switch. Okay, my address space stays the same. In this case, I do only one context switch. It is here. Okay, it is here. So the advantage for this one is I would save lots of CPU time wasted in the context switching. So both has, but in this case, if I am smart enough, in this case, if I implement my threads in the kernel space, if I am smart enough, I can favor this kind of a solution, because it is also possible with this kernel space thread. Using this scheduling is also possible. It is possible to have this or this or that. So the kernel space threads are more flexible in terms of scheduling. Okay, any questions? Okay, if there are no questions, then I will continue. We are going to look at a few famous process synchronization problems, two of them, dining philosophers and readers and writers problem, two very famous problems. The older version of the book, edition number 3, it has a full chapter on these problems. Okay, we are not going to look at them at that level. The new book doesn't pay that much attention to these kind of stuff anymore, because they are becoming more and more irrelevant, and the book is getting larger and larger. So this is a little bit different from last year's lectures. We will look at only 2 of them in a very small amount of time, maybe in 20-25 minutes we will be done. Okay, the dining philosophers. The dining philosophers, actually, we don't have any philosophers in the operating systems or any human beings at all. It's just an analogy. They say that they have 5 dining philosophers. They are eating their pasta. Makarna yiyorlarmış burada. Her birinin başında bir tane felsefeci var. Philosopher, Filozof var hepsinin başında. Yanlış yerlere koydum. Okay. Türkçe yazıyorum filozoflarda. Benim başına bir tane filozof var. So what these philosophers are doing is that they are thinking. Philosophers think that, right? They think. They don't do anything else. They just think, and when they get hungry, they eat their pasta. They eat their makarna yiyorlar. Çubuk makarna yiyorlar. Hem de yağlı çubuk makarna yiyorlar. That's why they need two forks. Okay? They need two forks. For this philosopher to eat anything, he needs to take this fork and start eating. For this philosopher, in order to eat anything, okay, he needs to take this fork and this fork. The problem is that these two cannot eat at the same time. Why? Because this fork is shared between these two. So when this one is eating, this one has to wait. Okay? When this one is eating, this one has to wait, etc. Okay? So the philosophers need two forks to eat. So this is a typical, this is a typical operating system environment. These are the processes. Okay? Okay? If you have a process and if you need two resources, one file to open and one file to write, okay? Open a file to read and open a file to write. And other processes can do the same thing. So if you are trying to open the same files, this kind of situation can happen in the operating systems, okay? So the files are your forks and the philosophers are the processes, okay? Processes. So this happens a lot. And we are going to see how this problem is solved and what would be the possible problems. Okay, so philosophers spend their lives eating pasta and thinking. Most of the time they think. Okay, they are doing something useful. They are thinking. If you think them as processes, then when they are thinking, they are producing something. When they are eating, they need to share some resources. They need to get some resources. Okay. When they are thinking, they don't need any resources. To eat, they need to pick up the fork on their left and right, and they start eating. So this one, E is eating, B is eating. C cannot eat because C cannot take this fork. Okay. So E, B, C. And EBC cannot dine, cannot eat at the same time. Okay, so this is a simple solution. This is a simple solution. It says non-solution. Philosopher I, let's say 1, 2, 3, 4, 5. Okay, in an infinite loop, they think when he is done thinking, take the fork I plus 1. Modulo n, so that it can take the first, of course, wrap around, okay? Then eat and put the fork, okay? So this is a non-solution. This is not a solution because, let's say, A and B, philosopher A and B started thinking together, and they immediately wanted to take their forks, okay? One of them took this fork, let's say B and C, okay? Okay. So, okay, philosopher A, okay. I am gonna P, H, I, B, and philosopher C. When philosopher B starts running, it takes this fork first, and C is running. C takes this fork, right? True? Yes. And then B is trying to take this fork. It is not there. And C is going to take this fork. It is there. So C is going to take both of them. So B will wait, right? Because it cannot take this fork. It cannot take this fork. So it looks like there is no problem. It looks like there is no problem in this case because C can continue eating and B will wait until C puts down the fork and it can continue afterwards. Okay, so it looks like there is no problem, but the problem is here. When all of them are A, B, C, D, and E. When all of them start thinking at the same time, okay, when all of them start thinking, when all of them come to this line at the same time. So each one will take, A will take this fork, okay, let me go this way. Okay, A will take this fork, B will take this fork, C will take this fork, D will take this fork, and E will take this fork. Okay, so they took their first forks and they are trying to take their second fork. A cannot take this one because it is already taken by B. B cannot take this one. C cannot take this one, D cannot take this one, and E cannot take this one. So what's going to happen? All of them are locked, and all of them are waiting for each other. So this is a deadlock. So it is called a deadlock. So this is causing a deadlock because we didn't plan it correctly. Because in this case, we know that all five of them cannot eat at the same time. Only how many forks are there? 5, right? How many forks are there? 5. How many philosophers are there? 5. So for 5 philosophers, how many forks do I need? 10, right? I need 10 forks so that they can eat at the same time. So that means that all of them cannot eat at the same time. How about 4? Can all 4 of them, out of 4 out of 5, can 4 eat at the same time? No, right? They cannot, because in order for 4 of them to eat, they need 8 forks. We have only 5. How about 3? Can they eat? Can they eat 3? No. So only 2 of them can eat at the same time, actually. So we need to come up with some kind of a solution that would allow only 2 of them to eat at the same time. Some people say that, okay, let's do it this way. They say that, okay. They say that. Let's put a semaphore here, okay. Let's say semaphore here, and down F, and when they put the fork up, it is up F. Okay? Does this solve the problem? When they are done thinking, when they are thinking, one of the philosophers will get the semaphore. It will down the fork. There is only one. Okay, maybe it should not be the fork. Maybe it should be lock. Okay, down, lock, up, lock. Okay. So it gets the semaphore. It gets the semaphore here, and when it is done eating, it ups the semaphore. Would this solve the problem? Yes.
Bir kişi yiyebiliyor sanırım burada sadece. Yani biriktikleri zaman diğer kişi çatal olamıyor. Olamadığı için de sadece bir kişi yiyor.
Yes, this is our mutually exclusive region, critical region. This is our critical region, and only one philosopher can be inside this critical region. As our friend pointed out, that means that only one philosopher can eat at the same time. Even though we have enough number of forks for 2 philosophers to eat, right? We can only one of them can eat at the same time. Okay, can eat at the same. So that's a problem. We should allow more philosophers to eat at the same time. So this was a problem defined in 1960s, beginning of 1960s, and Dijkstra, you know Dijkstra, right? I think he defined the problem, and he came up with a solution for the problem too. And we are going to look at that solution right now. So this is not a good solution. This is a solution, but inefficient solution. Okay, using the semaphores that way. I mean, making a mutual exclusion critical region is a solution. It works, but it is inefficient. We are going to come up with a solution that is both efficient and it doesn't cause any deadlocks or hangings or the data loss. Okay, so it uses semaphores again. It uses semaphores and some other data structures. Okay, we have n philosophers. To calculate left, I have this macro. Right, I have this macro. Each philosopher can have in either of these three states. Philosopher can be thinking, can be hungry, or can be eating. Okay, and we have a semaphore, and we have a state vector that can take one of these values. Okay. Our semaphore is actually a mutex semaphore, the one that I was using, and another semaphore array for each philosopher. I will have a semaphore that can be modified by that philosopher or by somebody else. Okay. So this is my philosophy procedure. Okay. In an infinite loop, thinks, takes forks, eats, and puts forks. So there is nothing interesting in this one. So I didn't do anything. So the important thing here is that take forks and put forks. These two have to be careful. When they take forks,